Hello guys, we will start today with this set of videos. I told you I was going to prepare for the analysis of electrical motors using this commercial tool called MAXWELL. Well, we will start today with the analytical design tool, but we will take also a look to some things that also appear when running MAXWELL 2D, as these radio buttons you can see in this small square. Okay, from all the things you can access from this series of buttons, let's say the only one that you will use is the materials database. MAXWELL includes a material database. It is quite complete, in fact, because it has the main components you may need to the design of any type of motor. You can see here we've got permanent magnet alloys. We also have all the types of conductors: aluminium, copper, graphite, for instance, for the brushes of DC motors, copper, cobalt, nickel, platinum, steel, iron, or in fact you can have all the type of materials you need. Here you've got the definitions of the different properties. You can check on this part the value of any kind of material. This may be useful even for things that are not in the scope of this course. If you need to find out something about materials, you can use this database. You can see also that for laminations you can have the BH curve. This BH curve is from standard iron and standard laminations, but you can also define your own magnetic material, and you can import and export all the things you put inside here. So, well, it is quite easy to make any type of design with this database. Okay, let's close everything and let's go now to open a project. In this display you can access all your projects done with MAXWELL 2D, 3D, or with analytical tool Rmxprt. Here you've got the directories where you've got your files. This is something you define when installation, and you can change it anytime you want. So, well, it is quite easy. In this case, I've got only two models. One model for finite element analysis and another model for the analytical design. In this case, I've taken the values of an actual machine. It is a machine that works in a similar way that a mineral mill. And what you can see here is the appearance. Let's put it in full screen. This is the appearance of a quarter of section of this machine. But this is not a finite element model. This is an output produced by the analytical tool that you have now to work on it if you want to play to analyze things with finite element analysis. So if you double click on it, let's reduce the size of this, even minimize it. You can go to the Rmxprt design tool. let's make this a little bit bigger, although it doesn't improve the size of this. Okay, we're now then inside the analytical calculation tool. This is a really simple analytical tool and really good because it produces very accurate results. As you can see, the design of an induction machine is done in 5 steps: general data, 2 definitions for the stator, and 2 definitions for the rotor data. Okay, email is annoying. If we go to general data, what we are going to work with is with the main data of the machine. You've got the rated output power, the rated voltage. You can change, of course, this voltage to the value you want, the number of volts, the frequency, the rated speed. The one you suppose is going to be the rated speed of the machine. You've got stray loss, frictional loss, the length of the magnetic core. This parameter here maybe sounds quite rare to you. This second factor is a factor to define the total length of the core that really is formed by magnetic material. It means that if we put here 0.95 from the total length of the core, only 95% will be magnetic material and 5% will be the insulation between the piled laminations that form the cores. 0.95 is quite normal thing. If you change this, of course, the efficiency, material consumption, and so on changes. Steel type is the type of iron you're going to use in the design of your machine. In this case, I've taken a standard lamination. Of course, you can use your own one if you define it in the material database, or you simply use the BH curve builder to create a new one. And I think it's not necessary to do it. Operating temperature, type of connection of the windings, and this is what you suppose your machine is going to work with. You can work with constant torque, you can work with linear torque, fan load, constant power, constant speed, or in this case, constant load. If at any time when you're working with this you get lost and you don't know what to put inside of these boxes, you can use the help of this program that is not really good in general, but is quite good for the case of the Rmxprt. If you go to 3-phase induction motors, you can see that you've got the definition of any of the different parts that will appear during your design. So in fact this video will help you to save time, but you can find all the important things here inside this help. It doesn't happen the same when you work with finite elements. If you try to use this help for finite elements, you will find that it is really complicated and no relevant data are implied. So let's go on, because this is very easy to understand. Stator 1. In stator 1 you define the general dimensions of the stator and you define the stator slots. You've got the inner diameter, the outer diameter, the number of slots, and then you design the geometry of every slot. If you've got different types of a slot, here you can see it changes the geometry. It takes a while to change. This computer is not very new and it has an old CPU, but you can see now they are all loaded that you've got different predefined geometries. For instance, this is the one you should use for a medium voltage machine, and this one is quite typical for low voltage motors as the one we are designing right now. All the things that appear below, all the things that appear below are defined here with exactly the same name. So by putting here different values, you can define different types of slots. In fact, I think that using the most approximate one to the one you're trying to define, if you've got a specific machine where you need to put a special geometry, you can do it just by defining different values here. Here in this case, this machine is an actual machine with a very simple slot, so you've got here everything defined. This part is the tooth width that you don't define because you define the slot and you know the dimensions, then it is not necessary to input the tooth width. Okay, so we've already defined the geometry of the stator slot. Let's go now to stator 2. Stator 2 is more complete than the previous one. In fact, in this case you have to define the arrangement for the winding and some other data. It is really nice because all the theoretical things we see during the classes appear here exactly in the same way. As you can see, we've got different type of winding too. You can have two possibilities for your own design of the winding. In number 10, you've got the possibility of designing single layer windings, and in number 20, you can design double layer windings. Of course, to do it you only have to follow the rules I gave you during the classes. So this machine is a machine with a concentric type coil, so we don't need to define anything. We only have to choose this type of arrangement. In the other cases, you see you've got different types of connection, but well, concentric is good enough. So this is the design we are going to apply. Well, let's go first to these parameters here. Top and bottom space areas in percentage indicate the amount of space you lose inside the slot because of the inclusion of protective layers or wedges and so on. So here you can put a percentage of amount of space that is usually lost. Well, In this case it is 1.5% because this actual machine I didn't know what was the actual value of these parameters. You can close this to a nil value, but it's quite normal to get a more accurate result to put something between 3 and 5% in the sum of these two parameters. This is the slot insulation measured in millimeters. This is the thickness of the paper you put inside the slot. And adjustment is the length of the end windings, what we call in Spanish las cabezas de bobina. Well, you can put here much more than 2 millimeters, but if you do that, you need to know how the winding is designed, and the changes that some reactances also change. You've got a conductors per slot. The coil pitch is pretty fine, so you don't have to do anything. You can also select a number of wires that are going to form any of your conductors. This is the diameter of the wire, and this is the thickness of the insulation of every wire. We are not getting on this last option, so let it define by user, and if you want to find out what it is, you only have to go to the help. Well, let's go then to the rotor. We can go now quite fast because it is exactly the same. You define the air gap, the inner diameter, and the slot dimensions. You can see here that you've got two slots, a top slot and a bottom slot. This is because this design program is also made for double cage machines. So if you've got a really pure double cage machine, you have to define an outer slot for the outer cage and a bottom slot for the bottom cage. So in your practical use of this tool, you will always use only one slot, so it doesn't make any trouble. If your rotor is casted aluminum rotor, you have to check this box, and don't forget not to check half slot, because then all calculations are made taking half of this slot. That's all. This second definition for rotor analysis includes some other things, but they are less common than the previous one. For instance, you can define things that are connected to the ventilation of the rotor. You can have axial holes, you can have a line duct, as I told you in class, and so on. In this case, we are not defining any ventilation hole, so we'll leave these two zero on this, and then these two things appear blocked. I've chosen a straight gate. This was just by mistake. It should be an skewed gate, but well, it doesn't make an important difference in the performance of the machine. If you want to play, you can also change the skewness of the gate here and play with the machine, running different simulations and so on. Well, end length of the bar should be what we in Spanish call cabeza de bobina para el rotor. It only indicates the amount of material that gets out of the magnetic core. It is between 5-8 millimeters and 20-25 if you're working with machines with powers rated between 11 and 30 kilowatts. This is the length of the bar. Of course, you know the length of the bar, the height of the end ring, and the width of the end ring. You must select the materials you're going to use, aluminium and aluminium. And okay guys, this is all you need to do to have completely defined your machine. So from this point you only have to run an analytical design that you can see it's really fast, even working on this old computer. And now all the data for your analysis are available under this post-processing thing. Well, this post-processor allows you to see all you've done from the very beginning. The first thing you can do is to have a look to your lamination to see if something has been done wrongly, or if you have not defined the number of slots according to your previous design, and so on. Okay, here you've got the total graph including your stator and rotor slots. Here you've got them in a larger scale. I think you can zoom in and zoom in and zoom out, and well, you can also get this to print if you want to include it as a part of your study. It is simply to show you how your machine has been designed. Well, you can also see your window layout. This is quite important if you are going to work with something you have designed on your own and you have not taken a predefined arrangement. Well, I know these figures here are really small. You will probably won't be able to now to see the numbers. So, well, but you can see the colors. Every color is one of the faces. But the most important thing is that you can, let me see. Well, you can arrange this. It's not very friendly, but my god, it's not very friendly, but you can now take a real and perfect look of what you've been done. If you don't want to play with this annoying thing of amplifying the image and so on, you've got here a summary of your window layout. It is done according to the rules we know from the theoretical classes, so you shouldn't have any problem. You've got the slot we call the in class input slot and the output slot. So coil number 1 is going to get the input in slot number 1 and the output in slot number 10, and it has 12 turns, so 12 turns will be inside any of these slots. Let's go again, and we are going now to something that is called design output. This is a purely text output, but it's really important because you can have here an incredible amount of information about your design. I'm not going to spend more time because If you are not sleeping at this part of the video, is because you are really serious people. So I will just mention the main things. You've got general data or data concerning stator, rotor, and something that is really interesting because you've got material consumption. You can know the total weight of the machine and the amount of copper, aluminium, and all other materials you are going to employ in the building of the machine. You can then make different designs and try to optimize the amount of material you're going to use in manufacturing process, because you are in industry, and of course the less amount of material you use, the most profitable is the design. Well, here you've got rated load operation, so this is very important too. You know, rated sleep, you can find out what a rated sleep is, power factor, efficiency, mechanical shaft, input and output power, stator current, magnetizing current, and so on. You also have no load operation, also very important to analyze the behavior of the machine, locked rotor, and the detailed data at rated operation. This is very important when you try to check your design in comparison with the design you will manually do. In your manual design, you will get values for stator tooth flux density, air gap density, stator teeth ampere turns, current density, that is around here, and you have to check the value that you get with this tool and the value that you calculate using our approximate analytical calculation formulas. And finally, you've got this that is called transient finite element analysis input data. You won't use this unless you are designing a finite element model of the machine, because in that case you will need to add to the model some external resistances and reactances that are calculated here. This is really useful. If you want to calculate all these parameters on your own, you will spend a lot of time. So if you try to make an actual design, something more serious, you will need to use all these parameters. Well, we are finishing, fortunately for you. We've gotten just now performance curves and these three other options that are related to concern, in fact, to finite element analysis. After running this simulation, you've got a geometrical model for finite element analysis that you can see here. This takes a little bit more time because, as you can see, it is a CAD design where a quarter section, it is a quarter section because it is supposed your machine is going to be symmetrical, so it is a quarter section of the machine. But anyway, I don't recommend you to use these quarter sections because boundary conditions are quite difficult to use. So if you want to play with finite elements, much better to play with the complete model I will give you. But well, you've got a tool, and you know you can work with this. It's an approximate section that then you will define materials and you can analyze by means of finite elements. you create MAXWELL 2D project, and you can also use another tool called Simplora, but it is not installed in this version. So let's go now to performance curves. Well, I'm only going to open one of them because I don't know how long I've been talking, but I'm sure it's been really long for you. And it is the same for all the cases, so I will just select torque curve. You've got current curve, efficiency curve, power curve. This is the power absorbed from the network, from the grid, and power factor curve. So let's go to torque versus speed curve. You've got this. It is not a beautiful design, but it is really efficient. All these options here allow you to make a zoom on certain parts of the curve. You can put a marker if you want to know the exact value at a certain point. For instance, here you've got a value. You can put a second one, and you can know the differences between one and the other. And by using these curves, it's the way you can analyze the behavior of your machine. Of course, I told you in the email I sent you that I want you to get these curves in the report you are writing, in the assignment you have to send me, just because it is much more comfortable for me to see the curves that are analyzing all the numerical values. Just the last comment, you've got here a calculator, but it is not a normal calculator. You can import signals, torque as in this case, and you can make operations with them. It is really useful if you pretend. You can also create equations. If your aim is to design complicate things and have a look in detail about this program, well, then it is quite important to know how to use this, but it is also in the help of the program. Okay guys, thank you so much for listening to me so long, but just wait for the MAXWELL videos and you will see this has been very short. Bye bye.